EMCO High Voltage Application Notes.
Hello, I'm Tim Thompson with EMCO High Voltage. I'm going to talk today about an application note, how to connect and test a regulated model. This application note will cover our CA series, our C series, and our H series models. Before I get underway, I'd probably like to make a little note about safety. Of course, whenever you're testing electrical circuitry, safety is of prime importance. You want to make sure you're aware of any exposed voltages and, of course, avoid those exposed voltages, and also make sure that everyone in your area is aware of their exposed voltages. Now we'll get into the application note. Our EMCO regulated models, first of all, I'd like to mention they're non-isolated models. That means the high voltage return is internally connected to the input return. So do not connect those externally. In fact, if you connect them externally, you risk inducing a ground loop. So it's best to rely on the internal connection for the high voltage to return connection. The regulated models are also highly regulated. The amount of regulation, of course, will vary from model to model, so you can consult your data sheet for the particular model in question. So to test a regulated model, you'll need a few pieces of test equipment, of course. In the application note, we refer to VNA power supply. That is our main input voltage power supply. That provides power to the unit to operate from. Of course, it needs to be rated to apply the appropriate voltage and input current as stated on the data sheet. So for whatever model you are testing, be sure you have a power supply capable of providing power to that module. The next piece of test equipment is what we refer to as V&B in the application note. That power supply applies the programming voltage. This voltage will adjust the output voltage proportionally, and it's typically a lower voltage. A typical range is 0 to 5 volts, and that has very low input current, so there is not a very high input current requirement on that power supply. Additionally, of course, you'll need a way to measure the output voltage. There are various options for that. We can use a high voltage resistor divider. We provide a model called a V1G that is useful in that application. And you would apply a digital multimeter to the high voltage divider to get an accurate measurement of your output voltage. Another option is to use a high voltage oscilloscope probe as an input to an oscilloscope. Another piece of equipment that would be necessary is a DMM to monitor the voltage monitor pin. Most of our regulated supplies provide a voltage monitor which will allow you to see a low voltage representation of the high voltage output, and that will be proportional. The ratio of the voltage will be dependent on the model, and again, that's an area you can consult the data sheet to find out exactly what that voltage should be. Finally, if you want to monitor how the unit operates in response to a load, you will need a load resistor. So in our demonstration today, we'll just use a dummy resistor in place of the load. In your application, if you have the actual load you intend to drive with the power supply, that would probably be preferable. But if not, you can substitute an appropriate load resistor. The key thing to keep in mind with the load resistor is that you must make sure the load resistor has adequate power rating and more importantly voltage rating, because we're of course applying high voltage to it. So that's a rundown of all the test equipment required. Next, I guess we can go through the demonstration, and for the demonstration I'll be using a CA20P model. In the application note, there are very good instructions for a generic application that you could use to test and connect any model, referring to the data sheet for the appropriate connections. But in this case, we'll go ahead and test a CA20P model. First of all, of course, we take the model, and you can refer to the data sheet for the connection pinout of the they show a good bottom view in there. So the first thing I'll do is connect the case ground to the input ground, and that is important for a couple of reasons. One, it makes sure the floating case, or the case does not float so it's not allowed to charge up to a high voltage, and then also it will help provide the EMI shielding. The next thing we're going to connect is the VNA supply, as it's referred to in the application note. That is our input supply voltage. I like to go ahead and monitor that with a oscilloscope probe, so I'll go ahead and connect that to the pin first. And then I'll use this ground bus to connect the return voltage, and that will go to the ground pin of the CA20P unit. The plus voltage out of the VNA supply will go to the input pin of the CA unit. Okay, so that is the VNA power supply. Now next we'll connect the VNB power supply, which is actually the programming voltage. As I mentioned, this will control the output voltage. So this will be, in this particular case, a 0 to 5 volt input will control the output from 0 to 2000 volts. Next we can go ahead and connect the output voltages to the output measuring devices. As again, in this case, I'll use two methods to measure the output. I'll use the DMM here with our V1G voltage divider to get a very accurate measurement, and then we'll also use a high voltage oscilloscope probe to measure the voltage on the oscilloscope. So first of all, the V1G, this is a 1000 to 1 voltage divider that is compensated in order to match the 10 mega ohm impedance of the DMM. So we can connect that to the DMM and connect the return lead to the high voltage return this time, and then we need to connect the high voltage output. I'll use a high voltage standoff here in order to make that connection, and then I want to make sure we connect the high voltage lead such that it can't short to the case, because of course the case is at high voltage ground. In addition, I wanted to demonstrate using a high voltage oscilloscope probe. So this is a typical high voltage oscilloscope probe. For that, I've already got it connected to the scope through its input module here, and I connect the ground lead of the high voltage probe to my ground bus here, and then I connect the positive lead of the high voltage probe to my high voltage standoff. So that's my second monitoring device there. As I mentioned, you can also monitor a low voltage representation of the high voltage output on the voltage monitor pin on the unit itself. So this is a scaled down voltage that is in proportion to the output voltage, and the ratio of that voltage will vary from model to model. So you need to consult your data sheet to know exactly what that voltage will be. In this case, it's going to be a 0 to 5 volt. So again, I clip the return lead to the ground pin and then connect the positive lead to the voltage monitor pin on the CA unit. So the unit is configured and ready for test. So now I can power up the power supplies, and an important thing to note is that your input voltage power supply must always be the first to be powered on, and there is a minimum of a 100 millisecond delay between turning on the input voltage and the programming voltage. Of course, with a manual test, that's easy to accommodate, but if you're doing an automated test where you're sequencing your power supplies through a computer system, you have to make sure that the input voltage is applied before the programming voltage. So we've got 0 volts on the input voltage and on the programming voltage. So now I can go ahead and turn on the input voltage and bring it up to the 12 volt nominal input. The CA20P will handle input voltage from 11.5 volts all the way to 15.5, and it will regulate the output voltage tightly within that range. So I'm just going to use, for the purpose of demonstration here, a nominal 12 volt input voltage there. So now we're ready to apply the programming voltage, and that will of course bring up our output voltage. But I typically will initially just bring this up in a slow manner to verify that my setup is correct. So now I have applied 10 millivolts on the VNB power supply, and we have a voltage corresponding on the output voltage meter. Again, this is 1,000 to 1, so 4 millivolts here would mean 4 volts on the actual output. And as I increment the programming voltage, the output voltage correspondingly rises. So this tells me that I have a valid setup and it's safe to go ahead and proceed. So now I'll go ahead and set the programming voltage to 1.25 volts, which is about 1/4 volt. That should give me 500 volts on the output. There, so with 1.25 volts on the programming voltage, we now have 502 volts on the output, so that's within the normal operating range. And we also have a corresponding voltage on the monitor voltage, and the ratios are set up in the CA20P such that the monitor voltage should track the programming voltage, but the monitor voltage is an actual indication of what the output voltage is, scaled down to a readable version. And we did get a deflection on the oscilloscope probe. Now at this level it's reading about 486 volts, so the high voltage probe itself has a calibration and a linearity factor, so that comes into play when you're using a high voltage probe. We're starting to read 10 milliamps of input current. Again, this is a no-load test, so our input current should be very low, so even at 1/4 output voltage we have a fairly nominal input current. So I will go ahead and set it to half voltage. So I'll set my programming voltage to 2.5 volts, and we can see we get a corresponding very close to the nominal 1,000 volts with 2.5 volts at the programming voltage. And again, the monitor voltage tracks accordingly. So finally I'll go ahead and set the output voltage to full scale. So with that, again on the CA20P, that would be 5 volts. I'll set my programming voltage to 5 volts, and now we have an output voltage in range for the nominal output of the unit. And here the calibration of the oscilloscope probe is accurate. I've got 2.00 kV on the oscilloscope. So the oscilloscope, typically an oscilloscope probe based on the sensitivity of a typical oscilloscope, won't be as accurate as the DVM, but that all depends on the accuracy you need for your own measurements. So next I'll go ahead and do the loaded test. Before, of course, I apply the load, I want to turn the output voltage down to 0. So in this setup, I can simply turn off my programming voltage, and you can see the scope reading goes back to 0. So our output voltage should slowly decrease. With no load, it'll take a few seconds to discharge the entire output voltage. So now I can connect my load. In this case, I just have a resistive load set up to the full load output of the CA20P, which ends up being 4 mega ohms. And as I mentioned earlier, we need to make sure the power and voltage rating of the resistors used for the load are capable of withstanding the voltage and the power that the unit will provide. In this case, it's 1 watt of power and 2,000 volts, so I had to use fairly high voltage resistors here for my dummy load. So now with the load applied, we can go ahead and turn on the programming voltage again, and we can see with the load applied, we return to approximately the same nominal output voltage within the regulation spec of the CA20P. So it shows the output is very tightly regulated. So of course, before you leave the setup, you probably want to turn off the output voltage to return the equipment to a safe condition. So I'll go ahead and turn that off and just set the programming voltage to 0, and of course drop our input voltage back down to 0 with the conclusion of the test. So essentially that's it for the demonstration. Thank you for your time and attention.
You'll find us on the web at emcohighvoltage.com.